Greetings. Well, it's my day off and I need to decompress because work was stressful. And today I'm going to use my time to talk about hop isomerization. Isomerization. Okay, hop isomerization. We're going to discuss the mechanism of hop isomerization. You know, it seems like brewers, we tend to discuss the rate of this reaction, we discuss the efficiency of this reaction, but I think we're much maligned to talk about its mechanism. And I don't know why, but I'm going to discuss it because it feels good. This occurs at wort pH, pH 5.5. This will also occur at basic pH. So let's just talk about the reaction, the straight reaction between water, alpha acid, and this reaction, the forward reaction, at wort pH is going to generate hydronium, H3O, plus A minus, the ionized alpha acid. And the eraser is the most useful tool when we're trying to describe, draw the mechanisms of these reactions. Your eraser is very valuable. All right. So at wort pH we have water plus our alpha acid, and we tend to think of these as Bronsted-Lowry, BL. Bronsted-Lowry acids and bases, where we donate a proton to water to make hydronium and the ionized version of alpha acid. Okay, so we're donating a proton in the case of a Bronsted-Lowry acid and accepting a proton in the case of a Bronsted-Lowry base. Very simple, very easy to describe this reaction. It describes the medium quite well, but it doesn't really describe the mechanism. Okay, in order to understand the mechanism or conceptualize the mechanism, we need to adopt the Lewis definition of acids and bases, and we'll see why. So again, we have water, H2O, and we're just going to draw molecular water, right? We're going to draw its two lone pairs of electrons. Okay, this is molecular water. Okay. And then we're going to draw alpha acid, and I'm going to try to draw this correctly. I'm also going to try not to drop my camera because this assembly that I've constructed is highly unstable, very high energy, and if I'm not careful, everything's going to fall and crash, but I should be good. Okay, there's alpha acid. All right, so we have a lot more information here. Here we have the Lewis structure of water, and we have the molecular structure of humulone. Remember, of the alpha acids, there are 5. We have humulone, cohumulone, adhumulone, pre- and post-humulone. The humulone is really determined by this R group, this little bit of organic spinach that's attached to this ketone. And this little bit of spinach undergoes no chemical change when this reaction goes forward. Okay. The first thing to note when we're discussing these molecular mechanisms, number one is nomenclature. Nomenclature. I think the Brits call it something different, but here in the United States we call it nomenclature. Okay. And so what that means is we need to be able to identify which of these functional groups are which. So these are hydroxy groups, and these are ketones. This C double bond O, and this C double bond bound to a OH group. These are ketones and hydroxy groups respectively. Okay. The second thing we need to note when we're trying to understand the forward reaction is electronegativities. Okay, electronegativities. This is a tendency of certain atoms on the periodic table to pull electron density towards themselves. Okay, this is really important when we're trying to understand chemical reactions. Okay, and I'm going to draw this hydroxy group this way, and there's lots of different ways to represent molecules. In this case, I'm just going to draw the covalent bond between the O and the H in this hydroxy group because it helps to conceptualize the mechanism. Okay, so we mentioned electronegativities. Oxygen is the most electronegative element in this molecule. There are more electronegative elements in the periodic table, but in terms of heme, oxygen is the most electronegative element. And what that means is we tend to pull electron density towards these oxygens. Okay, so we're going to pull it in when we think about this hydrogen. Okay, and we think about where hydrogen is in the periodic table. Hydrogen has a proton and an electron. Think about the electron and how it feels in relation to the oxygen to which it's covalently bound, through which it shares a sigma bond, and this oxygen out here through which it shares a hydrogen bond. Okay, so we're actually pulling at that electron from two different directions, making this hydrogen more electron deficient. Okay, in fact, it's so electron deficient that water is a strong enough Lewis base to strip it off. Okay, that's one thing that makes this molecule acidic. Okay, another thing we need to start thinking about is chirality. Okay, this is the three-dimensionality of this molecule. We have one important chiral center is right here. Okay, and this dashed line between the bottom of this molecule, there's a carbon there, this vertex carbon, which we don't draw for simplicity's sake. Between this vertex carbon and this OH is a dashed line, and that means that this bond is going into the plane of this piece of paper. All right, so it's going away from us. This solid wedge means that this vinyl group is heading out of the plane of paper, out of the plane of this piece of paper, heading towards us. Okay, so the way to think of this is a tetrahedron, where these two bonds going off this direction are within the plane of this piece of paper. This bond going off to the left is heading away from us, and this bond going off to the right is heading towards us. Okay, this kind of looks like that. Okay, so it's a good time to start thinking about the three-dimensionality, because the three-dimensionality governs the final conformation of this molecule. All right. Then finally, resonance. Resonance is very important. Okay, resonance. And that ends with a C, not an S. Okay, resonance. Okay, so one way to look at this system is a hydroxy, a ketone, and another ketone. Okay. Another way to look at it is through a ketone-enol tautomerism. All right. So when we have a hydroxy here, all right, and we're in a weak acid, right? Water is acting as our Lewis base, right? So what we're going to do is we're going to again represent this OH group like this, and we're going to draw water here. And what I've represented here is a 1,3 dicarbonyl compound. Okay, can't see it yet. Right now it looks like a hydroxy and a ketone. Right. Well, this is really a dicarbonyl, or this is an enolate form of it. So what we'll do is we'll have water acting as our Lewis base, stripping off this proton, which it's going to do here. All right. And what this will do is it'll create an enolate, right? Right? Where this charge is local to this oxygen. It's a local effect. But this is in resonance, right? And actually a better way to describe this resonance is with a single arrow like that. That's the way to describe it. And we can delocalize this one of these lone pair of electrons this way. Right? So now this negative charge is on the other oxygen, and all we've done was we've moved this double bond here, we moved this double bond here, and we move this double bond here. We can then draw an average structure, which would look something like this. where the double bond, the lone pair of electrons, is delocalized between these two oxygen atoms and these three carbon atoms. Okay? So it doesn't exist 100% in this state. It doesn't exist 100% in this state. Generally speaking, the most accurate way to illustrate this enolate, this ketone enol tautomer, where the molecule doesn't exist in one form 100% of the time, or in the other form 100% of the time. It exists in this average state. This is the best way to represent the molecule. Okay? So, and what this does is this stabilizes our conjugate base. All right, so let's go ahead and draw the conjugate base. So we have water, all right, and let's go ahead and remove these electronegativity arrows. All right. Okay, so we know that oxygen's electronegative now, and we know that our conjugate base is resonance stabilized, but let's see it in action. Okay. So there's our humulone. So again, water is going to act as our Lewis base. All right. So water is going to do the same thing it did here with our keto-enol tautomer. So water is going to strip off this proton. We know why it's acidic. This lone pair of electrons is going to go onto this oxygen. We're going to draw this molecule again. Okay, again, I'm going to try not to knock over my, very jury-rigged camera stand here. Okay, so here the charge is local to this oxygen. It's a localized state. All right, doesn't exist this way. In fact, one of the lone pair of electrons, it delocalizes through this molecule. It can delocalize one of two directions. It can either go towards this ketone oxygen or towards this ketone oxygen. So let's go ahead and just draw it very lightly. We can go down here and form a ketone, right? We then take this sigma bond here, and we can either go this direction, and we can take this pi bond, delocalize in this direction. All right. So we've delocalized this pi bond and this pi bond, or we can delocalize in this direction, this way, right? So let's draw the average structure instead of drawing every single resonance form. Let's draw the average structure. Okay. Now keep in mind, when we have a resonance stabilized conjugate base, that means the alpha acid that generated it tends to lower the pKa of the alpha acid that generated it. Okay? So as does this electronegative effect, this like resonance effect will also govern our pKa. All right? Okay, now this is the molecule that we care about. Now keep in mind, this water generated hydronium, which I hope you can see. There's hydronium ion there, okay? H3O plus. So, and then this whole molecule has the formal -1 charge, -1. Again, because we have electrons that are delocalized across this oxygen, carbon, 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 oxygen. So across 4 carbons and 3 oxygens, we delocalize to the whole sort of northeasterly portion of this ionized alpha acid. And this is the first resonance form. It's resonance stabilized, tends to lower the pKa of the alpha acid that generated it. Okay, we're now going to go through 2 transition states before we go to the cis and trans iso alpha acids. Okay, so let's start with the intermediate we just drew. And keep in mind, these intermediates do not last very long. They probably exist for like fractions of like a nanosecond. So, oopsie. Again, We delocalize the electrons this way. We delocalize these electrons this way. So this portion of the molecule is kind of like resonance stabilized, and we'll just give it a formal -1 charge. Okay. And I do have my little cheat sheet by me. Okay, and part of the issue here is just drawing these things. It just takes time. Okay, so this is our sort of the state of alpha acid that we're interacting with. The first transition state is what I'm trying to say. Okay, now keep in mind we have water and hydronium ion that are in this sort of equilibrium. All right, so we need a source of protons. Okay, so at the bottom of this transition state, we're going to have molecular water, right? And at the top of this transition state, we're going to have hydronium. Okay, plus. And this is a salt, so H3O plus and then alpha acid minus. Okay, this is part of what contributes to its water solubility. So what we're going to do, again, we're going to represent these hydroxy groups. And, if you look at this, you actually have more than 3 of these dicarbonyls that exist in this molecule. There's one here, there's one here, right? But there's also one here, right? It's all in how you look at these molecules. It's kind of a puzzle to figure out. Okay, again, we have water acting at the bottom of the transition state. Water acts as a Lewis base. This lone pair of electrons temporarily forms a ketone. This pi bond will then strip off a proton from hydronium, which will then generate water. Okay, so we have water acting as our Lewis base at the bottom of the transition state to form hydronium. Okay, we generally don't draw hydronium like this equilibrium, but this is what keeps happening. This is what's governing the forward reaction. Okay, so we have water acting at the bottom of the transition state, and then hydronium acting at the top of the transition state. That's our source of protons is hydronium, and our source of electrons is water. All right, we're going to erase this little guy, but keep in mind this equilibrium is what's driving this reaction forward. All right, this is an acid catalyzed reaction. It would occur in weak base too, but we generally don't drink that beer. All right. All right. All right. So what we're going to do is once we break this double bond here, this vinyl group is no longer constrained by the plane of this piece of paper. Okay? So once we break this double bond, this vinyl group is free to rotate. Okay? It gains a degree of freedom such that when we go from the first transition state to the second transition state, the second transition state forms with the vinyl group facing behind us. Okay? All right. And we temporarily form a ketone here. A little sloppy. Always keep in mind, the better the quality of your picture, the better you're going to understand this. So we're going to form a ketone at the bottom here. All right. Again, this part of the molecule is unchanged. We're going to delocalize electrons this way. I'm going to form a second transition state. Okay. And again, we're going to have a hydroxy group going off in this direction and a vinyl group going off in this direction, right? Okay. So this is our second transition state. Okay. Again, water acting as our Lewis base at the bottom, and hydronium acting at the top. You got it? This will be plus. All right, so we formed a ketone here, and this is temporary. We're gonna have again water acting as our Lewis base, strip off this proton from this hydroxy group. This lone pair of electrons was going to come down and form a ketone. This ring is going to condense. So we're going to go from a 6-membered ring to a 5-membered ring. And the ketone that we formed in the first transition state is going to be a hydroxy group in the second transition state. It's going to get its proton from hydronium at the top of the transition state, right? And now, when this hydroxy group forms, it's either going to form on the same side of this vinyl group, or it's going to form on the opposite side of the vinyl group. This is when we form the cis and trans iso alpha acids. Okay? And I'm going to try to move my camera a little lower here. Try to. Okay, so let's go ahead and condense the ring. Start with the vinyl group. We've got 2 5-membered rings. Boom, boom, boom. And this is humulone. Boom, boom, boom. Okay, so we either form the hydroxy group on the same side of the double bond, which is the cis isomer, the cis iso alpha acid. Okay. Boom. Okay, or we form it on opposite sides of the vinyl group. I'm getting so excited. Okay. We're going to move a little bit to the left here. There we go. Okay, and the opposite side. So we're going to have hydroxy group going this way, vinyl coming down this way. This is actually now a ketone. Boom. Okay, and this is trans. Okay, so the hydroxy group that we formed here is either on the same side in the case of the cis isomer, or on opposite side in the case of the trans iso alpha acid. So this is cis isohumulone and trans isohumulone. Okay, so we can see a lot of chemistry going on here. We can see we need to understand what functional groups are which. We need to understand electronegativities. That is, in order to predict the forward reaction, we need to understand chirality. So we understand the three-dimensionality of these molecules, as well as these various resonance forms. So in order to really understand this, we need to have a requisite knowledge of other areas in order to truly understand this mechanism. All right? But it's well worth studying, and I can think of no better reason to study organic chemistry than to learning how hops isomerize. So anyways, that concludes my little 25-minute presentation. Thanks. Bye.